right, and we're back. We're on the back of those Intro to Waves notes. A couple things to finish up before we're done with our little intro discussion. We were just talking about longitudinal and transverse waves. It's not really another type of wave, but it's something you might see. It's a phrase you might, a word you might hear. That is a wave pulse. Wave pulse is not like a repeating thing. It is a single short disturbance of some matter or a field. So it's like a little piece of a wave. Okay. The pulse can be either transverse or longitudinal. You can have either type. It's just one little bitty section of a wave in isolation. So it can be transverse or longitudinal. It travels in simply one direction through the matter or through the field. If, on the other hand, you have a whole bunch of pulses that are repeated at a regular interval, this is what we really focus on in here, then we have what is called a periodic wave. Periodic meaning it has a certain period to it. We'll get to what that means in our next topic. So, I've got a little app, no, not that. Okay, here we go. So, if I want to make a wave pulse, that's a wave pulse right there. There's another wave pulse. See how it's just one singular, it's one singular feature on a wave. It can be repeated at will. I can do a whole bunch of different ones at once. I can even change the size of them. Okay, they don't all have to be the same size, but they are just one singular, one short disturbance. On the other hand, if I want something that oscillates over time, I'm going to put this normal. This would be a periodic wave, something that repeats over and over and over and over again at a regular interval. Let's go back to pulse. Okay, so we're going to draw some pictures of pulses on our notes. You can have a pulse like those pulses were all triangular pulses. You can have a pulse that looks like this, nice and rounded. You could have like a square pulse. You could have a triangular pulse. You could really have whatever you want, okay? These are all examples. You can call these examples of transverse wave pulses. Now, you might be wondering, well, how do we draw a longitudinal pulse? Okay, when we draw longitudinal waves, you know, I used the Slinky before, but the Slinky's not great. Here's how we draw. Here's one way you could draw like a sound wave pulse, maybe like a really short sound, one little vibration. Okay, these lines, and we'll talk about what these lines mean later on, but these lines can represent like the fronts of sound waves, and a pulse would maybe be something like this. And then we're back to normal. Okay, it's one disturbance right here. You can think of this kind of as like showing kind of like the pressure. The sound waves are all just air pressure variations. The pulse part is right here, okay? It's a single short disturbance, where right here there's a higher air pressure than the places around it. So this might be how you show a longitudinal pulse, a longitudinal wave pulse, okay? The speed of the wave or the pulse, it says pulse, but it could be speed, wave or a pulse, depends on the medium it's in. That's very important, okay? The speed depends only on what type of material the wave is passing through. Some mediums allow waves and pulses to travel faster than others. For instance, light travels much, much faster through air than it does through water. Sound is actually the opposite. Sound travels much faster through water than it does air. Okay, so light travels faster in air than in water. We'll have a whole day specifically about sound waves when you guys come back from this little 5-day break. When a pulse or a wave encounters a different medium, so when it goes from, let's say, air to water, or if the way I do this in class is I have two Slinkies and I hook them together, and I say when it goes from the thin Slinky to the thicker Slinky, there's three things that happen. You're going to kind of have to take my word for it, because I can't really demonstrate this one. I do have one picture that I can try and show you. I'll erase this and then I'll show the picture. Go. Okay, let's see this picture. So these are, these are light, beams of light. They're coming off of a laser over here. I know you probably can't see this very well. Maybe I'll turn off the lights for just 1 second so maybe you can see a little bit better. These are lasers over here. They're different lasers. The red and the green doesn't really matter. What I want you to focus on, they're hitting a prism right here, and yes, they're reflecting all different ways, and we will talk about this. But what I want you to focus on is right here, where it goes from air into this new material, this glass. Okay? You can see very faintly, well, maybe you guys can't on the video, but very, very faintly right here and right here, you can see part of these lasers, which are just light waves, okay, very focused light waves. They're getting reflected, okay, down this way. Okay, they're hitting this glass, they're reflecting down. You can also probably definitely see that some of that light is passing through. So we call that being transmitted. And then probably, if there was a way to add up the amount of light that you see here and the amount of light you see here, I'm guessing it probably wouldn't exactly equal this. In other words, I'm saying some of this is probably getting absorbed. So I'm showing you this so that we can talk about what happens at a boundary. At a boundary between two different media is the plural, excuse me. When a pulse or a wave encounters a different medium, three things will always happen. Okay? Part of that wave will be transmitted. In other words, it will continue, can't spell, transmitted. It will continue into the new medium. And I'm going to draw a picture of this. So, we're going to have kind of a separation here. Let's say we have tied two strings together, and we have a wave traveling on these two strings. So here's the thin string section. We have a wave on a thin string traveling this way. Okay, it gets there. And then over on this side will be our wave on a thicker string. And I'll draw that in just a second. Okay, so what's going to happen is at the boundary, some of the wave is transmitted. D. Some is reflected. And some is absorbed. So, getting ahead of myself a little bit. Part of the wave is transmitted. That means it continues into the new medium. Part of the wave will be absorbed at the boundary. And if what happens with that means some of the energy will be lost. Okay, some energy will be lost. Some energy will be given off here. Okay, because remember these waves are carrying energy. That's why we use them. We want them to take energy from place to place. So what that means, even if some of that wave is transmitted over here on the thicker string, perhaps we're just not getting as big of a wave as before. Okay, this is my show of how it's a thicker string. Okay, hopefully you can tell that that's a greater thickness. It's kind of fun drawn. Nope. Spoke too soon, I'm not very good at this. There we go. Hopefully you can tell that that's thicker. But you can also tell that it's a smaller wave. Okay, we'll talk about this in a little bit, but the amplitude of this wave is smaller. It's not as big of a height. Okay, so the wave was transmitted, but it's also not as big. Some of it was absorbed. And then finally, part of the wave will also be reflected back into the original medium. So what that means is, even as this wave is moving along, you might see part of a reflected wave traveling along back in the other direction. Okay? So those are the three things that can happen at a boundary. Now, the reason that, because something a little strange happens when it gets reflected. We have to talk about what happens at a boundary. Okay? At the boundary, what usually happens to the reflected part of the pulse or the wave, it could possibly be inverted when it comes back. Okay? See how this wave was kind of coming down and then it flips and it goes back the other way? That's what we mean by inverted. Okay? It will invert if it meets what we call a fixed boundary. Fixed boundaries, such as a wall or any other type of material that doesn't vibrate very well. Okay? And here's a little picture. Well, let me show you. Here, I'll erase this. I'll show you with the little computer app what I'm talking about, how we know that it flips. This thing is nice because it shows fixed boundaries and also movable boundaries, which we'll get to in just a second. So let's put a fixed end down there. Okay, we got a clamp. This part of the string will, or the wave will be held. Let's send a pulse. Okay, I'm gonna let go a little farther. Now it's a fixed end. We should expect this pulse to flip. I'm going to put it into slow motion, and we're going to play it. And we see that it does indeed flip. This also acts as a fixed end, by the way, so it should flip back up to the top. And if we let this go, it'll just keep flipping over and over and over again. Okay. Well, what if we make it a loose end? Actually, no, we'll do this first. What if we make it a loose end? Now, instead of having it clamped here, I have a little ring that can slide up and down. So watch what happens here. It gets reflected back with the same orientation. This is still a fixed end, so that'll flip. It'll invert. When it gets to the ring at the end of this time, it stays the same. So we'll just keep doing this. So there's a difference between what is called a fixed boundary, that was with the clamp, and this says loose end. We usually call it a movable boundary, or a movable end. So let's draw this out. Okay, so at the boundary, the reflected part of the pulse or wave, maybe inverted. Okay, we did that part. So let's say you have a pulse coming towards a big wall, okay, which is fixed. Pulse comes in. What ends up happening? Pulse will go back out inverted, all right, if it hits a fixed boundary. If, on the other hand, it encounters a boundary that can move, the wave will be reflected right side up with the same orientation. Okay? And the example for a movable boundary is just imagine that you got kind of like a little ring that's on a pole. This will slide. I could get into the mechanics of exactly why this one flips or why this one inverts, but we don't really have to do that for the sake of the Regents course, which is kind of nice because it does get a little tricky. It has to do with forces, but it will rebound right side up if it's a movable boundary. The last thing that I want to talk about for this particular topic, it's a question that comes up on the homework a decent amount. And it's one of those things where you just have to practice it. You have to get good at reading what is going to happen to an individual piece of a wave. When you're looking at the wave, it's important to be able to tell which direction a piece of matter or field will move in. This depends not only on the type of wave, it also depends on the direction that the wave is traveling in. Direction of travel. Okay, so I'll give you an example of this. All right, we got our little wave flipping around here. Let's see here. Let's try this. Bear with me for just a second. All right, there we go. I'm going to erase this now. So, I'm going to have you draw something very similar to this in just a minute. But what we essentially have right here is we have kind of almost like a full, we would call this a wavelength, okay? One full cycle of a wave, up, down, and back to the original spot. So I want you to think, we're going to let the wave pass this little dot right here, this little green one, okay? And I want you to try and predict what's going to happen to that green one. Which direction is it going to move in as the wave gets to it? So now, the wave, we know, is traveling in this direction. So because the wave is traveling in that direction, then what we can say is, well, this lower part of the wave is going to reach this part first, right? So what should happen is this little dot should slide, as the wave itself, you know, the wave isn't the individual pieces. The wave is kind of the disturbance. As the wave keeps passing to the right, this will undergo the downwards disturbance first, and then it will move up as this part of the disturbance gets to it, and then it will return back to normal. So let's see if that whole thing happens. We put it in slow motion, down. Oh, that's really fast still to look for it. Anyways, it did go down, and then it went up, and now it's returning back to its original spot. We can actually, let's just let this go for a little bit. You can look at it coming the other way too. Coming the other way, and I'll keep doing, click by click. We think it should go down first, and as a matter of fact, it does. It goes down into that trough, that's what it's called, as it moves past. Now it's going to go up onto the crest, and now back to its original spot, okay? And we know this is a transverse wave again because all these pieces are simply oscillating perpendicular to the direction of wave travel. Right now this wave is traveling in this direction, but all the pieces are oscillating up and down, like this, okay? And it'll flip here. Now we'll go up first, and then down, and then back to normal, okay? So, if you're given an example like this, and you're told the wave is moving this way, and you're asked, how will A move as this wave passes it? As wave passes A, will move down, then up, and then back down to its normal spot. Okay, this part will get to it first, so A will follow the path down in. Okay, it'll go down. Then it gets to the crest, it will rise back up, and then it will go back to normal. Likewise, you could see something a little bit more complicated. What if you had something like this, and you were asked what happens to B? You have to know the direction of wave travel. I would say that B is going to rise up as this part gets to it, rise up again as this part gets there, it'll fall way down, and then it'll rise up back to its normal spot as the entire wave passes through. So, as wave passes, B will move up, and then down, and then finally up one more time. Okay, that's one of the trickier wave questions for some people get. Some people get it very easily right away. Like I said, the best thing you can do is just practice with it. I'm going to stop that video right there. This is the first set of videos that you'll see. And I will be back later. Bye.